Okay, let's, oh, look, there are lots of people waiting in the front row to talk to us. That's excellent. But before they're allowed to talk to us, I have to introduce their chair. So the chair of the last section of our symposium is Jill Penridge. Jill is the Associate Director of Operations for Tern. She started in January this year and has a wealth of experience across, knows just about every university in Australia through various methods, which we won't go into. So I'm just going to introduce her. Thank you.
Thank you, Beryl. All right, last session of the day. We're almost there. This one's a good one, though. So Tern's vision for the future is to advance ecosystem science and contribute to sustainable management of Australia's environment. That's our context. We've heard a lot of ideas about the future from the last 2 days, and each of the speakers coming up today in this last session is going to be addressing those opportunities and challenges that come from modelling, forecasting and predicting in a different way. They've all got their different take. So there'll be some time for Q&A at the end, so keep sending those questions through the app or emailing Beryl, beryl.morris@uq.edu.au. But now I'm going to ask Sebastine to kick us off for the last session. Thank you.
Hello, my name is Sebastine. I work with CSIRO, and I'm working on the next generation of soil landscape grid of Australia. For those of you who might not know, the landscape grid, soil landscape grid of Australia is the primary or foundational data set of soil information for the entire Australian continent. Is a suite of raster for different soil attributes and functions. It maps this attribute to the 2-meter depth. So we have standard depth intervals, for example, from 0 to 5 centimeter is 1 layer, 5 to 15 centimeter, you go that way up to 200 centimeters. So what is currently available with the soil land grid of Australia is just a static information. You just have one map representing, for example, soil organic carbon or soil pH. But we know that sometimes some soil attributes like soil organic carbon change with time, whether due to climate, natural dynamics, like in climate, in vegetation, variability, and also land use, land cover change, contribute to changes in a soil attribute like soil organic carbon. But it's very, very essential to know where the soil attribute change, especially for some a attribute like soil organic carbon. What is a big deal about soil organic carbon? Carbon sequestered in the soil, in the terrestrial ecosystem, is more than carbon stored in vegetation and the atmosphere combined. So it's very, very important that we measure and continue to monitor how the soil organic carbon change because of greenhouse gas emission. So in my previous work, I did a space-time modeling of soil organic carbon using machine learning to predict for every year for the entire Australian continent. And we've published the work in Geodama already. This is the workflow of the work. So we applied to Tern. We've got funding from Tern to improve the work further, refine it, make it better, and it becomes a product. So that is what I'm currently working on. So this is the workflow of the space-time mapping of soil organic carbon for the entire Australian continent. So basically, we have a soil profile data set for taken at different points in time. We collect them from different agencies. I think Tern have got some through the Australian Soil Federator. And this soil measurement have got dates and also sampling date. If a soil measurement doesn't have sampling date, it's of not much use to us. So it's very important that it's got a date of sampling as well as the coordinate. So we link this data set to this covariate, or what we, in simple parlance, predictors. Among our predictors, to make this a space-time soil modeling, we divide our covariate into two. We have dynamic covariate, for example, climate and NDVI. Then we have static covariate, for example, slope, terrain attribute. And yeah, in the initial phase of the work, we also use mean climate condition and vegetation condition. But whichever one we use here is not reflected in the dynamic covariate here. So we match, for example, for any point, the date of measurement, we go use the coordinate, extract the terrain, the dynamic covariate and the static covariate. For that date, we look at our the dynamic covariate. We go back 10 years back in time to retrieve the dynamic information. And we use this decay function to aggregate the 10 years of data. So data that are of more recent, the data that are of the dynamic covariate, for example, rainfall that is more recent is weighted highly, whereas the one that is 10 years ago is weighted a little bit low. So that is the way we incorporate dynamic information into the model. So here we build a space-time cube, and we do the modeling, then predict for everywhere across Australia. And we didn't just do prediction, we try to explain, because many people, one of the arguments people have against machine learning models, they consider it as black box. So here we applied what we call Shapley index from game theory to disaggregate for every of these predictors. We map what the contribution is to the prediction. So these are some of the initial results. Okay, this is the modeling, the data. These are the distribution of the data in space, whereas distribution in time. So here is the model where we evaluated the model. It's fairly satisfactory with least concordance of 0.69. And here is where we map the importance of each covariate. And interestingly, I think many people have been talking about this fractional vegetation cover. Okay, 1 minute, oh my goodness. So fractional vegetation cover, photosynthetic vegetation, it came out as the most important covariate. You can see the magnitude of its impact on the prediction is quite high, is quite large, more than all the other predictors. So we also develop, and this way you can visualize this is for every 10 years of the soil organic carbon, and this is a trend map. So here we map each of those covariate or group of covariate, how important they are. For example, vegetation plays a greater role in predicting soil organic carbon. So here is just comparison with process-based model. ROTC is the model for soil organic carbon in the Australian full carbon accounting with some observed data set. And I think our prediction looks nice for this location, it's comparable. So I have an app a rudimentary app to assess this information. And so these are for two locations and the trend. So as time progresses, and I see Tern has got that facility to visualize a data set. Hopefully, when we finish with the product, people will be able to access and download the data. Thank you.
Hi, my name's Nathan, and I am the coordinator of the Australian Mountain Research Facility, and I work down at the Australian National University. And my predecessor in this role, Zach Brown, introduced this, our infrastructure when it was newly deployed about 2 years ago at the same event. And I'm here to talk about, in the time since, how we're thinking about the future of Australia's mountains and how we're using our infrastructure to support predictive science and apply lessons learned and how the design of our infrastructure supports this type of scientific investigation to meet the special needs of this unique region within Australia. So for some background, just to set the stage, Australia's mountains are unique globally, but also within Australia. They are biodiversity hotspots and have been very important to the First Nations peoples of Australia for thousands of years, but are also very important to the lives and livelihoods of people living in that region today and all across Australia. They contribute greatly to Australia's economic output through ecosystem services, providing large portions of water to downstream catchments like the Murray-Darling Basin, but also to recreational opportunities in local economies in that way. These values are vulnerable to change because of the unique geological and biological conditions that combine to make this area so unique. And those values are already changing and will continue to change in the future. In order to inform adaptive management and science in this region, we need to take into consideration the special needs of this region. And we need to design infrastructure to address those needs. And we can take general lessons from similar infrastructure that Tern and others have supported historically across Australia, but we also need to talk within the researcher and community that have been undertaking research in this region for a long time. And in 2020, there was a LEAF grant that helped establish the facility, and the design that came out of that was one that was meant to address the needs of research groups across many disciplines and across jurisdictions. And in general, in order to address these and investigate the different parameters that are going to be undergoing change, there's sort of three general things that we need to address and knowledge gaps we need to fill. The first one is addressed by monitoring, and it's because this region is sort of unique in many aspects, it's been historically underrepresented in data sets. And so setting up long-term monitoring to help characterize more completely the baseline trends and emerging trends as time goes on. We also need to have experimental setups to help probe species level and community level responses to these emerging trends and changes. And then we also need to replicate this sort of infrastructure across space and time in order to integrate it together and capture not only local heterogeneity, but also generalize those things to capture trends on a landscape level. And that's sort of where the Australian Mountain Research Facility came into being. And this is sort of language that comes from the very beginning. And I'd like to highlight, improving predictive capacity is sort of the core mission of this infrastructure, grouping of infrastructure and the people behind it. And just as a quick introduction to our sites and infrastructure, we have sites located across jurisdictions throughout Southeast Australia, in Victoria, ACT, New South Wales, and in Tasmania on a variety of national park land and private landowners as well. So we have close partnerships with those people. we also, a core to our monitoring, as I addressed before, monitoring is sort of one of the major core pieces of infrastructure that is provided by automatic weather stations, measuring contextual soil, groundwater, depth, soil moisture, precipitation. We have also a few flux towers in our network that's providing data about not only local conditions and carbon dynamics, but also feeding into the OzFlux network, providing national, international context as well. And then another core piece of what we do is provide experimental infrastructure to support students, researchers, and others to probe not only what's going on right now, but what will go on in the future, because this is an area that's a region that is undergoing change very quickly, and because of its geographic isolation, there's not much capacity for relocation of species, and a lot depends on their adaptive capacity in and around that region. So to address that, we have a series of infrastructure that, for example, FutureClim, very important piece of, it's a factorial experiment that simulates both warming and drought by simulating about 4 degrees of warming in soil comparatively to ambient conditions. So it's capturing natural variation in a way that you can't in a greenhouse. And similarly, we have DroughtNet and deployable heat wave chambers that you can take to different regions and simulate heat wave events as opposed to long-term warming in mountain flows. This is similar to FutureClim. It's allowing us to simulate warming in surface waters. And so sort of over the last few years, we've seen how these have been used to investigate and predict future trends, and then also feed back into decision-making to address these coming changes. I'd like to highlight some research that's being done by a very prolific team of hydrogeologists and geochemists utilizing our mountain observatory across many sites in New South Wales, Victoria, and ACT. They're using our series of soil moisture probes, groundwater, and snow depth monitors to map residence times and pathways of the water through the landscape, and it's revealing things that we were not aware of coming into it, and you might not generalize from other mountain regions around the world. Down in Tasmania, we have work being done by Mark Hovenden and others at UTAS cataloging carbon dynamics in subalpine grasslands, and they're finding that these grasslands have great potential to continue storing carbon, but current conditions have them on a knife's edge. So it really, local interventions retaining water on landscapes that have been historically drained may have great potential to retain that ecosystem function. And to highlight FutureClim again, we support a lot of ongoing and past student projects, PhDs, looking at all sorts of interactions that we can use to probe the thermal tolerance limits of native species, soil microbe changes, and also this coming year we're looking at outplanting different provenance snow gums to see if there's local populations that are more resistant to warming and things like that. So just quickly, we believe that this is a tried, tested deployment of very robust field-tested equipment, and we believe that there's great promise in being able to continually use this and also serve as a model for growth and demonstrate that it's not only just the individual sites and individual projects, but the feedback that they give across the landscape, feeding back into each other to investigate this very unique landscape and across Australia's high mountain environments. Yeah, thank you. And if you're interested in getting to know more about us, there's a link here, as well as the Australian Institute of Alpine Studies has a newsletter where you can get connected to the larger alpine research community in general. Thank you.
Set myself a timer here. Cool. Everyone can hear me? Good. Howdy. I'm Drew Terasaki Hart. I work at the CSIRO. And this talk, let me go forward actually. 47 years ago, Simon Ferrer gave a talk yesterday, more or less. This relates back to that. So this is part of a larger project that Simon, Andrew Hoskins, Chris Ware, and I are working on at the CSIRO to try to essentially leverage as much strength as possible out of kind of the deluge of observation-only biodiversity data coming in from things like iNaturalist and eBird to understand biodiversity patterns. And in order to do that, I'm going to walk you through briefly some software we've been building to simulate species assemblages and their observations across environmental gradients that we'll then use to validate the modeling frameworks we're building out around the larger project. So the motivation, one more time, there we go. What we wanted was to simulate realistic alpha, beta, and gamma biodiversity patterns as a function of environmental gradients. We wanted software that would simulate then observation processes on those data, or on those patterns, really on the communities that kind of underlie those patterns. And then also simulate changes in those patterns as a function of environmental change over time. And all of that, like I said, the idea being to then validate the modeling framework we're putting together to use on real-world data. What exists right now wasn't really ideally fit to our workflows. Things like niche and virtual species are great pieces of software, but really didn't fit into the exact software framework or conceptual framework we were going for. And some other simulators are out there, but kind of overly complex for what we wanted to do, like RevoSim. And so we decided to roll our own. And what we're making aims to be a minimalist, user-friendly, flexible, and extensible framework for simulating all the things I mentioned above. And therefore, we aimed for an object-oriented, for the programmers in the room, approach by developing essentially a Python package that we can plug into our broader workflows. And importantly, because these simulations we expect when we scale them up will take some time, we wanted this to be easily parallelizable as well. So those are sort of the parameters within which we're designing this thing. And now what I'll do is actually kind of walk you through this big, ugly slide that kind of lays out how the thing is put together. If you're all still awake at the end of this slide, the rest of this should be pretty peachy to understand. So how does this thing work? Really 3 major steps. First, we parameterize the thing by inputting a handful of raster data, essentially. So a raster kind of specifying the potentially spatially variable alpha diversity, so spatial variation in the total amount of species in a place, as well as some other, the gamma diversity as well, the total number of species across your entire fake landscape. Some other minor parameters I can get into in conversations later, as well as a stack of layers, rasters like you've been seeing for the past 2 days representing the environment, whatever aspects of the environment in your particular use case would be driving diversity. And then also a number of functions. So for anyone who's used generalized dissimilarity modeling, GDM, that's the inspiration here. Essentially a bunch of functions specifying ecological turnover as a function of turnover in your environmental variables. And again, I've color matched these to these layers because each one would match up to a particular aspect of the environment represented by your raster. Once you have all those parameters put in place, relatively small number, simple parameters, step 2 is that we actually simulate species on the landscape. So for each species from 1 to gamma, your total target there, we simulate first the species niche. This is modeled as a normal distribution, so this is sort of a MacArthurian concept, but also kind of a mashup with a Hutchinsonian niche model in the sense that the niche is specified as a normal distribution along a set of normal distributions along each of these environmental axes, where the center of the distribution is drawn at random from the landscape, with the alpha diversity raster determining the probability of drawing it at any place, so essentially structuring the number of species falling in different places on the landscape. And the sigma, the width of that niche, is then essentially a rescaled function of the steepness of this curve. So where the turnover in ecological communities is quicker with environmental change, or environmental distance, I should say, niches will tend to be narrower, is the essential implication of that. Multiplying that by the range of your environment scales essentially every species niche to somewhere in your environmental space. And then we also describe the species using a couple other parameters. So lambda sub s here is the maximum abundance a species could, on the distribution that abundance is drawn from, at the center of its niche, and also things like probability of detection, allowing us to actually simulate the sampling process we're interested in. Third step, and I'm going to step back through a little bit of that, the core conceptual piece in just a second. Third step is that we simulate communities. The main thing here is for each site on the landscape where we're simulating a community, we're drawing the probability of presence of a species as essentially the probability that any given site's environmental value falls within that species' normal distribution niche. That's what this long, complicated thing is supposed to note. And once we have that probability, we draw the abundance either as 0, if a Bernoulli draw, a coin flip on that presence probability is 0, or as a multiple of the Poisson distribution and the probability of presence if that coin flip is a 1. So what the hell does all of that mean? Here's a couple species models to give you an idea. This broader orange curve would be essentially more of a generalist species. This tall, steep one would be more of a specialist. This is essentially how the species is modeled as a niche. And then the niche model is assessed at a given point on the environment, wherever you happen to fall. And the area in the tails, greater than, at least as big as or greater than that environmental difference, gives you the probability the species is there. So at this particular place, this specialist species is more likely to fall there than this generalist species might be. Now we've simulated communities across the entire landscape for all of our sites. And finally, really quickly, we simulate observations. And this is pretty simple. The observation probability can be a function of the relative abundance of the species in a site, the probability of detection that I mentioned above, as well as effort. So this allows us to then simulate anything from a standard ecological census in the field to presence-only observations like iNaturalist. That's the long and short of it. So these last few slides will show you what's coming out of the model so far. So again, here's our environment as a very, very simple geometric set of gradients producing things like this. This is a single instance of a species. Here's the species niche center and the expected distribution, the probabilities, where that species actually falls on the landscape. And we're simulating, thousands of species like this, so essentially, entire communities. And the results of that generate alpha diversity patterns that roughly map onto what we input in any given particular scenario, as well as the outputs of things like a GDM, generalized dissimilarity model, that show general kind of biodiversity turnover as we'd expect. We can throw noise into those. So same results you just saw, but with some spatially autocorrelated noise, starting to look a lot like real world patterns. And lastly, we can then simulate on top of this environmental change. So for example, let's say this middle, there's my pointer, environmental variable has some value added to it over time because of, say, climate change, an increase in temperature, and that increase is higher at higher values than it is at lower values. So say something like in the previous talk, accelerated climate change at higher elevation. We would expect our GDM model to catch that, and it does. And you can see we're fitting, these are splines, essentially recovering the ecological turnover with environmental turnover we input at the beginning. And you can see this sharp inflection reflecting the fact that we're now actually capturing added environmental space and the increased biodiversity turnover in that space as a function of community turnover across the landscape. And that's largely driven by species like this one, whose distribution is largely constrained by this center environmental value and expands pretty vastly across that space as climate change or environmental change takes place. So The outlook here, example applications. Our immediate goal is to validate our model, as I mentioned earlier, but we think that this will have use for a bunch of other purposes, assessing, say, sensitivity and effectiveness of methods, anything from species distribution, joint species distribution models, to other methods based around presence-only observations, like I mentioned. And importantly, it's a work in progress. We aim to publish a Python package soon, but we totally welcome interest from potential users, collaborators. I very much welcome critiques on any of my half-baked math. I'm not a mathematician. Please reach out. I'll be around after this, and we'd love to chat. Thanks.
Okay. Good afternoon. I'm speaking on behalf of a group of people who come from Tern, from the Tern Data Discovery Portal, and Miranda Fittock from UQ, and I've got a foot in each camp. So we're going to talk today about a particular subject. So it's a bit more basic than the previous presentation, I must say. We're going to talk about a historical data set that was established at this particular semi-arid site in 1926. And you can see this today. This is a Google view, nothing fancy. It's a approximately 390 hectare enclosure to keep out vermin. So in 1925, it was fenced. At the and in 1926, the first measurements were made. As you can see, kind of quite nicely. I can tell you which one that one is later. The records were kept very meticulously, handwritten in filing cabinets in the University of Adelaide in the botany department initially. And in 1990s, a D-based database, if anyone is old enough to remember those, I know a couple of people do, was created for much of the data. And by 1998, an access database was created. And I'll talk in a minute about people who are involved with this, because that does matter. However, in 2014, in the Wild West days of Tern, picking up on Rebecca's words, which I rather liked, much of the data was transferred from the Access database to Tern. And what we're talking about now is the 2025, that is this year's, update of those data in Tern. Now, it does have a trajectory that is quite important, and we might reflect upon 100 years' time from now for the data that many of us have been talking, or many of you have been talking about in this Congress. Basically, it was set up by T.G.B. Osborne, who had a great idea. He was in Adelaide for about 5 years. He went to Sydney very shortly after this establishment. It was then followed through, particularly by particular champions. And Dr. Constance Erdley, one of the first female academics, of course, one might say, in ecology and taxonomy, carried it through with great passion and diligence, bringing lots of students, and as you can see from here, into the reserve and keeping the measurements going. Then Russ Sinclair, who you can see here, came into the picture. You can see there are some gaps between these timelines, but anyway, Russ Sinclair came into the picture, and he, with even more passion perhaps than some of the predecessors, I did meet Constance, he really pushed Cunamore forward, as they often call it. Now we are at an impasse. Despite this, the work of Jose Facelli, who has been mentioned previously in this workshop, and David Ladd, who's the technical officer for the site, they have kind of carried forward as interim custodians, but we don't have any more named at the moment. And when I say we, I'm not part of the University of Adelaide. I do consider this pretty of national interest. So I can say we. Okay, so this is what it was about. It was a site for monitoring change after those vermin were kept out. Now, I might mention that the place was pretty well bare. It had been sat upon by cattle, eaten out by sheep, and really was bare. and that does relate to the creation of these particular quadrants called fire quadrants. Various quadrants were established, but the fire quadrants were set up in 1928 as a means to stimulate seed germination and release a bit of carbon from the litter that was kind of there, though there wasn't much of it. So there were 31 quadrants that have been monitored in this data record from 1926 to 2014. This is the record that's in Tern. 73 photo points with 892 images, to be precise, that range and with observations to accompany them. Observations of photo points start in 1907. One of the photographs was followed till 2000. One of the photo points was followed till 2008, so I'm being generous in that time frame. Of course, rabbits had to be followed, but interestingly, they weren't, at least the data available only ranges from 1977. Kangaroos, thanks to Andrew Smith, Professor Andrew Smith, who some of you may know, set up with Bob Lange in 1968. We've got some of those, but you can see some of the ideas there. We've got more, and you can think of some of these super sites where people come in and out and measure things. There was certainly that. These are these are sites that we have data in Tern, openly available, but were set up because of particular interests at the time or observations. There are some trials, and of course we have the transects. The transects were set up in 1928 or something, but the data have been lost, and this was a revisit in 89. So it is a bit of a story of opportunity, accident, and translation. Now, was it worth it? So we have to talk about this first. 52 scientific papers, many of which emerged, I suppose the majority actually, I should analyse that, emerged from PhD projects, honours projects, master's projects, and independent research projects. 9 theses. There are a few people whom you may know who did their PhDs or their masters on this and honours on this site, and of course many, many field trips and teaching opportunities. We got a bit of a jump there. We do have some insights. Now, these graphs are from the Tern data, the data that are available in Tern. And please note that as of last night, I didn't go to your celebration, as of last night, and I didn't do most of the work, Aaron and a few other people did, wow, we have the data up in Tern. You can see here with Myoporum and Senna that there's a hell of a lot of change. We needed 100 years to really, or nearly 100 years, to see what's involved. This is the 100th anniversary of this site, and there is a big celebration being carried forward at the University of Adelaide. So different sorts of observations. Some of the most, I suppose, interesting from our point of view at the moment is that the photographs have actually been released for open use onto Tern, and we'll just run this little, there it is. And here's an example of photo point 6, and this is for Baptiste. The tree fell, okay? But anyway, and it's still there in 2000. It fell in 1952, and it is still there, observable in 2008. So there you go. You can get lots of things. Okay, I'm going to go run a little bit over. Okay, so isn't everyone? Okay, so really the insight for the future is this is the classical data workflow organised slightly differently. And look, you've got all of these things that we really, think matter. Standardisation, we've heard about it. Vocabularies, data recording, everything like that. Metadata, controlled vocabularies. Having a partnership with Tern where your data is going to be carried through and looked after and updated with fair practices. The actual problem with a long-term site like this is internally transferring the information over 80 years, let's say. And don't think that 20 years is long-term. It ain't. as far as Karunarathna is concerned, they're pretty good at collecting data. I wouldn't say their standardisation was great. The rest of it, without the help of Tern, I don't know, and some passion by individuals, it would have been very difficult to say this is a celebration of 100 years. Okay, that's the end of it, but I will say thank you very much and encourage you to come to International Data Week and to a co-located meeting where we will talk a lot more about data repositories and carbon use, etc., of storing all these amounts of data that we've got, but also to train people up through that data workflow so that we can actually look forward to another 100 years. So thank you very much.
Good evening to you all. I'm Nishan, a PhD student from the University of Queensland. Before starting the presentation, I would like to mention that I'm not so good in English, so I'll be using my note whenever I want. So as part of my PhD, I develop and evaluate various multivariate forecasting approach for improving the inference and prediction for ecological count data, especially for the species abundancy. So over the course of my research, I explore several potential modeling approach. However, not all of them could be included within my PhD thesis. This presentation is based on such approach. It is really a simple idea, but it's helpful to improve the forecasting accuracy. Still, there are some challenges, so I am seeking the clarification on them. So that is the main purpose of this presentation. I truly look forward to your feedback at the end of this presentation. So, you know, when we want to select an appropriate model, we have to look at various aspects. For example, the objectives, data structure, nature of the response variable, and predicted, and so many. And another important aspect is the form of the response variable or the outcome variable. This study is mainly based on this aspect and test whether the forecasting accuracy depends on the selection of the response variable or the form of the response variable. Assume we are interested in estimating the abundance of a particular animal species in a given area and how this abundance fluctuates over time in response to climatic and environmental changes. Then we can select multiple sampling plots and record the number of animals along with the relevant environment data at regular time intervals. The number of animals recorded can be used as the response variable for modeling purpose. This gives us several observations for each time point. In this kind of situation, the common practice is obtaining a single response value for each time point for using the univariate approach for forecasting purpose. As the responses, we can use several measures like sum of the counts or the average number of animals per plot or any other appropriate measures. This data aggregation helps in capturing the overall trend, but it leads to loss of information. This can limit the model ability to detect patterns and reduce the accuracy. Therefore, it is more often beneficial to keep the response variable as much as informative. For this, in this study, I propose an approach by accommodating more informative information to response. Instead of relying on a single univariate response, I expand the univariate response into multivariate form by deriving 7 summary measures, namely the minimum, first quartile, second quartile, third quartile, maximum, sum, and average per each time point. By treating these measures as a multivariate time series response, they are modeled together. Due to this expansion of this response variable, we get both advantage and some challenges. Some are here. The key challenge is the transformation of the distribution of response variables, as it makes the modeling process more complicated. So I will explain this briefly. If the original data response, if the original responses is in the continuous scale, then the derived response is also in the same scales. Then without any difficulties, we can model them together by using the multivariate normal distribution. But if the original responses in the discrete scale, then the derived measures will be in both discrete and continuous scale. That makes the modeling process difficult. So we have to deal with different type of distribution in a multivariate form to accommodate their interdependency structure. Anyhow, this is a more critical point, so I addressed this issue in this analysis. So the main goal of this study is to assess whether including multiple derived responses can improve forecasting accuracy compared to modeling of average or sum alone. To explore this, by generalizing this idea, I model each series independently and jointly by using the simplest model, that is the autoregressive model of order 1 in both univariate and multivariate form. Here I use these three distributions: negative binomial for the minimum, then normal for all the quartiles and the average, and Poisson for the max and sum. So here, in both models, the value at time t is modeled using the lag value at time t minus 1. Here I didn't consider any correlation structure, that is to understand the impacts of lag predictors clearly. For this analysis, I used the rodent abundance data from a long-term monitoring project in Arizona area in the North America. This study has recorded the monthly count of a rodent across 24 sampling plots along with the climatic and environment variables for more than 5 decades. As the outcome variable, I use the total number of rodents across all species in each sampling plots. Now let's move to some key results. These two figures illustrate how well each model captures the pattern in the observed value across the training and testing periods, which are on the left and right side of the vertical red line. During the training period, both models show the predicted value that closely follow the observed data, indicating a good fit. However, in the testing period, forecast of the univariate models deviate significantly from the observed value, while the multivariate model captures the variation more accurately. To further assess the prediction and the forecasting accuracy, I used two measures, that is root mean square error and the mean absolute error. They were calculated separately for each series under each model. Overall, the multivariate models provides lower value, that's mean lower error for both measures for most of the series. These matrices were also computed for the training and testing period separately. While both models perform similarly during the training period, the multivariate model produced lower values during the testing period. These results highlight the forecasting accuracy of the multivariate model is higher than the univariate model. To understand the interdependency among these derived series, I examined the coefficients of VAR model obtained from the posterior distribution. Here the values at the time t become the response and the previous value become the corresponding predictors. So this analysis indicates that all the derived response depend on their previous value. These the distribution on the diagonals indicate that. And in addition to that, some measures depend on the previous value of some other series or some other measures. So for an example, if you look at this one, the sum at the time t depend on the max at previous time point and the average at the previous time point. And if you look at the average, average is depend on maximum value at the previous. So this indicates the presence of interdependency among these series and the importance of accommodating them to improve the forecasting accuracy. Conclusions. So this indicates that joint modeling enhance the forecasting accuracy compared to the modeling the sum of average alone, regardless of the associated complexities and the challenges. However, the use of this will be depend on our objective. So if the objective is forecasting, then this should be more appropriate. And the model the approach I use could be used in many occasions, as we have to deal with mixed type responses variable. So this could be used in many occasions. And I expanded this with many other models, but I have not added any results from these because I wanted to just compare whether the modeling of mean or average along will be better or will be bad compared to joint modeling of them with other measures. I think it is clear. So these are the challenges. So here, first I try to model with a single series, then there were so many zeros, then I consider six species, then also I got so many zeros, so then I consider all the species, and in addition to that, the model formation was difficult in this Tern because I use a Bayesian approach, and the prior determination and the distributional transformation, those are the challenges I face. And if we look at the limitation, so far I have tested this with one data set, and I have accommodated only 3 distribution and consider only the autoregressive model of order 1 and consider only 2 measures for testing the accuracy of the forecast. And here I have considered only the short-term forecasting and many more. So these are the actually clarifications I need from the audience. I know theoretically this will be wrong, but we can get some improved forecast if we follow this procedure. So I would like to know the audience opinion on these matters. So thank you so much.
All right, I'll ask our panel to step on up. I'll let you go too early, sorry. We've got some questions from the audience. All right. If you're happy to kick off, I'll ask your question first, if that's all good. Great. So, question from the audience. You're working on overcoming the weaknesses of forecasting, which is a big challenge, so that's great. Could you apply the approach that you've talked about to a well-known forecast that failed and use your method to demonstrate better accuracy? Is it something you think you could apply in the future? Do you have an example where you think it might be useful?
Yeah, of course, because actually my main purpose was modeling the responses that follow the different distributions. For that purpose, I used this data set. So in real situations, we have to deal with multiple responses in different types. So definitely we can use this one to get improved prediction in many occasions, as we have to deal with several type of responses together.
Great.
Yeah.
And so it might have applications in ecological science, I imagine, in a bunch of different ways. Are there any examples that you've thought of already?
Actually, my main purpose was to generalize this method, this approach, to develop the tools for fitting this kind of model, including the data generation, then fitting different kind of model, and then testing their prediction accuracy and everything. I thought of generalizing this as a kind of package, set of tools to handle these kind of task. Yeah.
Yeah, great. I'm going to stay a little bit on topic. Drew, question for you. So you mentioned open access, easily uploaded software. To ensure that true democracy of access, would we need to have multiple language options for the front end, or maybe pictograms?
That's an interesting question. What is a pictogram, first of all?
Great question. Why don't we go with the first part? So for the front end, I guess the GUI.
Yeah, I mean, I imagine once we've got the thing built, fully validated, it would be pretty easy to add wrappers around it for people working in something like R or other common languages. The pictogram part is interesting because I could imagine things like this also have a lot of educational value, and I can imagine wrapping kind of there's sort of like visual point and click kind of program builders online.
Or user tutorial style.
Yeah. So yeah, I think there's a lot of potential there. It'd be fun to, whoever asked to, I'd be happy to chat with them more because that'd be fun to explore.
Have a go. Cool. Nathan, I've got a vested interest in this question because I live on a mountain. It's a little mountain compared to the ones that you're talking about, but it's still a mountain. Do you think that the non-alpine and alpine observation sites have that sort of transferability of the findings that are coming through with the work that you're doing at AMRF?
Yeah, I think that's definitely something that we're wanting to look at in the future, because as it stands, our sites actually exist across a local gradient, because actually a lot of them are at montane and subalpine. So we're already capturing a bit of a local transect in that sense, but I don't see any reason why it couldn't continue to capture a latitudinal one as well, because there's mountains all up and down Australia. So the very local conditions about the snow dependence and that kind of stuff is kind of specific to parts of what we do, but there's no reason why we can't sort of generalize the setups and things to address other local questions at other points along that gradient.
Yeah, cool. And have you got any key findings or interesting observations that you can share about the future CLIM sites? That's something people have asked about.
Currently, a lot of those PhD students are kind of in their last years and they haven't drafted the theses yet, so I won't scoop them on that. But the performance of the infrastructure has been remarkably good at maintaining. We maintain a 4-degree soil warming at depth, so it tracks a control plot and then warms to the temperature of that control plot, and we keep track of that temperature, and so it's capturing variability and not just sort of warming without consideration for what the environment's doing.
And quite unique as a research tool, I imagine, research infrastructure.
Yeah, because we've got 5 replicate blocks, so there's lots of, and it's supported a lot of students in like a small amount of area, so they've been kind of working on program or projects at the same time. So people are taking soil samples at the same time that people are taking carbon measurements. And so those students have their own projects, but the data can be used together to look at how the carbon leaving and entering the grassland manipulations is also co-varying at the same time in the same place with the things in the soil chemistry and the microbes and things like that. So lots of like potential data sets can be built from that. But right now it's mostly individual projects.
Yep, awesome. Last question goes to you, Alison. Sebastine had to get on a plane, as I'm sure some other people in the room, so we'll have to keep it short. But would you consider there are parallels between Coonamoor with multiple custodians and contributors with hurdles likely to face in citizen science projects? Is that transferable?
Well, that's a nice parallel in a way, because although it's a university, it is a bit like a citizen science project of researchers who've had that sort of, who've provided the continuity. Yeah, absolutely. Champions and gatekeepers are a classic description for citizen science projects, and while that champion's there and effective, then it works. But as soon as you have that lag phase, of course, you've got to educate, and we were hearing about some of the education material here today. You've got to educate to make sure the team is there, but you really have to have a succession plan, and that was one of the things that has been obviously difficult, and we've got a problem now with the continuity, but for sure there must have been one before. It isn't evident in the data particularly, but one wonders after a while, if you are sharing citizen science data, for example, how trustworthy that data are, or those data are, sorry.
Fantastic. Well, we're a little bit over time, so I'm going to call a wrap there, but can we give our panel a thanks? Always hard going last, and I'll hand back to Beryl to wrap us up.
Thanks, everyone. And I know that everyone's got somewhere to go tonight, but I've got three important things to do. I'm not going to give a summary of the symposium. It was an incredible smorgasbord of everything, and I'm going to need to watch the recording again. All I know is that I have taken away the idea that ecosystem science is alive and well, and it's great to be a supporter of all of that research. So well done to everyone, all the presenters. You've done a fantastic job. And I'm also needing to thank all of the chairs of the sessions who tackled all the handling of the questions. Andrew, for being our patron again. We look forward to seeing you in 2027. Of course, we've had a wonderful library venue and the museum last night, and Kaigi is our event organisers. But what I really want to do is drag out from the back room, because I see them scurry out for food every now and then, but the people who've actually worked so hard behind the scenes. So can you open up the door, and even if you don't come down here, at least come down the stairs a little bit. Mindy Gilling. Nico Rako-Tapare, Jaden Hausfeld, Peter Brady, Jill Penridge, Isabel Serron. Come on, you can come down a bit further. Well done. It's a wrap. Safe travels home. Thank you.